All right, so we'll be solving a physics question paper. The course code is 9702, and the variant is 21, October, November 2015. The first question tells us, state the two SI-based quantities other than mass, length, and time. So in AS level, we have learned 7 basic quantities. Among them, mass, length, and time are some of the base quantities. Other than that, we can mention temperature, and then there is luminous intensity, there are actually a few more. There is current, and there is amount of substance, and so on. So basically, you can mention any 2 out of these 4 quantities. You also need to know the units of these quantities. You might be asked to write down the units as well. For example, the unit of mass, the SI unit of mass is kg. For length, it is meter. For time, it is second. For temperature, it is Kelvin, and so on. For luminous intensity, it is candela. For current, it is ampere. For amount of substance, it is mole, right? Okay, so moving on to the next question. A beam is clamped at one end of an object X, is attached to the other end of the beam, as shown in figure 1.1. So we can see a beam that is attached to this clamp here, and there is an object that is placed at the other end of the beam, to which the attachment is. So the object S is made to oscillate vertically, which means it's being moved along this direction, the vertical direction, up and down, up and down. The time period T of the oscillation is given by, so if we're given with this equation here, T is equal to K root over mL cubed divided by E. We are to show that the SI base unit of Young modulus is kg meter to the power -1, second to the power -2. So in order for us to show the SI base unit of Young modulus, we must know the formula for Young modulus, right? Young modulus is symbolized with capital E, and it is the formula for Young modulus is stress divided by strain. The formula that defines stress is force by area, and the formula for strain is the extension divided by the original length. Okay, so just for a recap, let me conclude, Jay, how I am approaching a math like this. So basically what I have to do is whatever quantity I am given with, in this case, Young modulus, I am to write down the formula which defines that, right? So Young modulus, for example, is equivalent to stress divided by strain. Then stress again can be written as force divided by area, whereas strain can be written as extension divided by original length. Then we look out for more ways in which these formulae can be defined. For example, force can be written as mass into acceleration. Area can be written as length into breadth. Extension can be written as extension does not need to be further broken down into other formulae, and neither does original length. So we can just right away write force can be replaced with mass into acceleration. We can also keep area as it is because we already do know the unit of area, don't we? Extension divided by original length. Okay, great. Now, let us figure out what the SI unit of mass is. The SI unit for mass is kg. That for acceleration is meter second to the power minus. So these are things that we need to know by heart. For area, it is meter square. For extension, it is meter. And for original length, it is meter again. Right? So how about we start by canceling out any unit that we think can be canceled out. For example, this meter can be canceled out with this meter. Kg meter to the power, meter second to the power minus 2. Do you see how if we shift meter square from denominator to numerator, this becomes meter to the power minus 2? Yes. So kg, you see how this meter and this meter, they have the same base, right? These two. So we can write meter to the power 1 minus 2, second to the power minus 2. This is just simple mathematics. Kg meter to the power minus 1, second to the power minus 2, because 1 minus 2 is minus 1. That is why, that is how we get minus 1 here, right? All right, so the SI base unit of K therefore is this, and it has been shown, right? Okay, the SI base unit of Young modulus is this, and it has been shown. In the second part of the question, we are asked to determine the SI base unit of K. So since we are asked to find the SI base unit of K, what is K? K is a constant that we find in the equation for time period that is already given in the question. So I will be copying this in the whiteboard since I don't have much space here to write. Or maybe, yeah, I think it would be better to copy this in the whiteboard, yes. So let us go to the whiteboard. Let us copy the equation that is given in the question, which is T is equal to K root over ml cubed by Young modulus. So see, we already know the SI unit of Young modulus, right? And that is kg meter to the power minus 1, second to the power minus 2. Great. So since we are to find the SI unit of K, the first thing that we are supposed to do is subject K. And what exactly does subjecting K mean? Subjecting K means keeping K on the left-hand side and putting everything else on the right-hand side. So can we write K is equals to T divided by root over ml cubed by Young modulus? We can, right? So now that we have subjected K, we start with listing down the SI units. For time, the SI unit is seconds, so we write S. For mass, it is kg. For length, it is meter, so we write meter to the power 3. For Young modulus, the SI unit is this whole thing that we found just a while ago. That is kg meter to the power minus 1, second to the power minus 2. Now let us see if we can cancel out a few things from here. We can cancel out kg with kg, and that's it. So if we bring these two from the denominator to the numerator, if we transfer this becomes meter to the power meter to the power 4, second to the power 2. This is just simple math, the math that you do with indices. So not breaking it down. This can be further written as, see, this root over here is literally to the power half, right? So you have meter to the power 4 here and second to the power 2. So when you multiply this half with these powers, that becomes meter square and second, right? So we can write meter to the power -2, and this second, they cancel out. And that leaves us with the unit of k being meter to the power -2, right? So we can go back to our question paper, and we can just write that the SI base unit of k is meter to the power -2. Of course, you need to show the workout. I'm just not showing the workout over here because I don't have space. I did it in a different place. So yeah. When we're done with this, we go to this next question, which says that data in SI units for oscillations of X as shown in figure 1.2. We are given with the quantities T, L, M, and K, time, length, mass, and the constant K. The values are given, and the uncertainties, the respective uncertainties for the values are also given. So let us see what the question asks us at first. We are asked to calculate the Young modulus and its actual uncertainty. Okay, so the Young modulus value goes here and the actual uncertainty goes here. The SI unit is given. Okay, so let's get started. First things first, if we are to find the value of Young modulus, again, we know how to do it. We have to use this formula, right? That is given to us. That is T is equal to K root over ML cube by E. So if we are to find Young modulus, we of course need to subject Young modulus, right? So T by K, and again, what does subjecting mean? Keeping the letter to be subjected at the left-hand side and everything else goes on the right-hand side. So T by K whole square ML cube by E. So we can just write E is equal to ML cube by T by K whole square. If we further break this down, it's ML cube by T square K square. All right. All right, so let us find the actual uncertainty of T at first. So in order to find the actual uncertainty of T, we take the percentage uncertainty, which is 2% in this case. And we multiply that with the power of T, which is 2. Plus, we take the percentage uncertainty of L and we multiply it with the power of L, which in this case is 3. So times 3 plus, we take the percentage uncertainty of M, which is 0.1, and we multiply that with 1, since the power of M is 1. And then we take the percentage uncertainty of K, which is 1.5, and multiply that with 2, since the percentage uncertainty, since the power of k is 2, and that gives us the total percentage uncertainty, or you can say the percentage uncertainty of E. All right, so this gives us the percentage uncertainty of Young modulus. Now we use a calculator to find the answer. 2 times 2 plus 0.2 times 3 plus 0.1 plus 1.5 times 2, which is 7.7%. Now we keep that as it is and go back to this part to find the value of Young modulus. So the value for M is 0.2068. So we take 0.2068, we multiply that with the length, which is 0.892. There's a cube, and then we take the value of k, we square that. It's 1.48 times 10 to the power 5. And then we take the value of t, we square that as well. It's 0.45 square. Okay. I am going to insert this in the calculator to see what I get. 0.2068 times 0.892 cubed times 1.48 times 10 to the power 5 whole to the power 2 divided by 0.45 squared. And that gives me 1.587608812 times 10 to the power 10. Okay, now to find the actual uncertainty of E, I need to multiply this value with 7.7 and then divided by 100. So basically I am finding out 7.7% of E to get the actual uncertainty of E. All right, so the actual uncertainty of E, what I mean is Young modulus, is given by 7.7% of Young modulus, which is 1.587608812 times 10 to the power 10. Now, how do we find that out? We multiply 7.7 with 1.587608812 times 10 to the power 10, and then divided by 100. And the value that we get is 1,2,2,4,5,8,7,8,5. Now, it is important to keep in mind that uncertainty, as an actual uncertainty, should always be expressed in one single digit. In that case, the single digit here is 1. If we round this off, we get 1 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 to the power 9. The unit is kg, meter to the power minus 1, second to the power minus 2. All right, this is the actual uncertainty. And the value that we get here is 1.58, a lot of digits, times 10 to the power 10. Now, how are we going to write this as an answer in this space? It is very important that we make sure the power for the value of Young modulus and the absolute uncertainty is the same. So instead of 10 to the power 9, I'm just going to write 0.1 times 10 to the power 10, which is basically the same. This value and this value is the same, right? I'm just making sure that the power of the absolute uncertainty and this is the same, right? So the next thing we are supposed to do is make sure that the number of decimal places of my absolute uncertainty and the number of decimal places of my value here are the same, which means that if this is 1 decimal place, so should this be 1 decimal place, okay? So if we round this off to 1 decimal place, it will be 1.6 into 10 to the power 10. So what we can write now is 1.6 times 10 to the power 10 plus minus the absolute uncertainty, which is 0.1 into 10 to the power 10. Okay, I will recap this a little bit, which means that I have to make sure that I find the percentage uncertainty at first, which was 7.7 of and this is the percentage uncertainty of Young modulus. And then we find the value of Young modulus by subjecting Young modulus, which came which turned out to be 1.58760881 times 10 to the power 10. And the next thing I did is find the actual uncertainty of Young modulus, which is 7.7% of the value of Young modulus. And that turned out to be 1 into 10 to the power 9. And then the next thing that I made sure is the power of my absolute uncertainty and that of the value should be the same, which is 10 to the power 10. And then I made sure that the decimal places of the value of absolute uncertainty and my value of Young modulus must be the same. So I rounded off 1.58760881 times 10 to the power 10 to 1 decimal place, which is 1.6 into 10 to the power 10. And finally, I got my answer. So that's it. Now, moving on to the next question, which is question number 2. The signal from a microwave detector is recorded on a cathode ray oscilloscope as shown in figure 2.1. The time-based setting of the CRO is 10 picoseconds per centimeter. Determine the wavelength of the microwave. Okay, so if we are to determine the wavelength of the microwave, we need to know the speed of the microwave first, right? Since microwave is an electromagnetic wave, all electromagnetic waves have the speed 3 into 10 to the power 8 meter per second. The time-based setting is 50 picosecond per centimeter, which suggests that 1 centimeter is 50 picoseconds, right? And if we count the number of boxes that are covered by 1 oscillation in order to find out the frequency, 1, 2, 3, 4 1 centimeter boxes, right? So basically 1 oscillation is covered by 4 1 centimeter boxes. So we can say that the time period is 4 times 50 picoseconds seconds, right? Which is 200 picoseconds. And from here, I can find out frequency, which is 1 by d, and that is 1 by 200. Instead of picoseconds, it would be better to convert picoseconds to seconds at first. And we know that in order to convert picoseconds to seconds, I have to multiply by 10 to the power minus 12. So that would give me the frequency. 1 by 200 times 10 to the power minus 12 should give me 5 into 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the power 9 hertz. So since I know the frequency and I also know the speed, I can use the formula V is equal to F lambda to find out the wavelength lambda. So subjecting lambda, I get V by F. The speed is 3 into 10 to the power 8, and the frequency is 5 into 10 to the power 9. So my answer is, I know it's a bit clumsy down there. Okay, let's just write the answer here. Since it's clumsy, I'll just write the answer here. The solution to 3 into 10 to the power 8 divided by 5 into 10 to the power 9 should give you 0.06 meters. All right. And that is the answer. Okay. Now moving on to the next question, the signal from radio wave detector is recorded in the same CRO. The wavelength of the radio wave is 1.5 in 10 to the power 3 meters. Determine the time-based setting required to display the same number of oscillations on the CRO. So we need to find out the frequency in this case and then the time period. So V is equal to F lambda again. F is equal to V by lambda. The speed is 3 into 10 to the power 8. And the wavelength is 1.5 into 10 to the power 3. The frequency, therefore, is, if we insert this in the calculator, we get 2 into 10 to the power 5 hertz. Okay. So, we can find the time period using t is equal to 1 by f, which is 1 by 2 times 10 to the power 5. And that is 5 into 10 to the power minus 6 hertz. Okay, so for so if 4 centimeters displays entire wavelength, oh, wait, I think I wrote the unit incorrectly. It should be seconds. So if 4 centimeters represents 5 into 10 to the power minus 6 seconds, since one entire wavelength is covering 4 centimeter or 4 1 centimeter boxes. So I have to find out how much time is being covered by one box or one 1 centimeter box, right? So 4 boxes covers 5 into 10 to the power minus 6 seconds. Therefore, one box covers 5 into 10 to the power minus 6 divided by 4 seconds. So that should give me 1.25 into 10 to the power minus 6 seconds. Okay, I can also write that as 1.25 milliseconds, or yeah, I think that's the best way to write it, because 1 millisecond is 10 to the power minus 6 seconds. So yeah, if you just multiply 10 to the power 6 to this quantity over here, you should get the answer in milliseconds. So 1.25, and the unit is milliseconds. Okay. Oh, there's another thing that I need to tell you, that is we always write either in the lowest sig fig of the raw data, the answers, or in the lowest sig fig, or one more than the lowest sig fig of the raw data. So in that case, if we write it in the lowest sig fig, in this case, the lowest sig fig of the raw data is 2 significant figures. Like if you check this out, it's 2 significant figures. So I can just write 1.25 rounded off to 2 significant figures is 1.3. Okay. Keeping it as 1.25 is correct also, so you can do it either ways. All right, moving on to the next question. An object is moved from point P to point R either by a direct path or by path P to Q to R as shown in figure 3.1. P and Q are on the same horizontal level. R is vertically above Q. Explain whether the work done moving the object against the gravitational field is same or different along paths P, R, and PQR. Right. All right, so the answer to this question, you can refer to the definition of work done here. We know that the definition of work done is work done is equals to the force applied multiplied by the distance moved by the object on which the force is applied in the direction of the force. So since the object is moving the same distance while it travels from P to R, and while it travels from P to Q to R, as it is moving the same distance. So we can say that, yes, the work done is the same. So there are 2 points here. One point is that you are to define the work done. It is the product of force applied multiplied by distance moved in the direction of force. And then you need to be clear that the distance moved in the vertical direction, sorry, the distance moved in the vertical direction is the same as the distance moved in the direction of the work. Since gravitational force always acts in downward direction, you basically do no work while you are moving from P to Q, right? So even if you move along this direction, let's say, from P to Q, and then from Q to R, you're ultimately only doing work while you're moving from Q to R. So you should basically forget about the PQ journey, because no work is being done by gravitational force here. All right. The gravitational force acts vertically, therefore you only should consider the vertical direction. And the same goes while you move from P to R directly. When you're moving from P to R directly, you're basically getting displaced from here all the way here. So again, you have to consider this distance only. So this distance here and this distance here are the same. That is what I want to say. And therefore, the work done is also equal. Okay.